work?
Today it's related rates,
Okay.
and it's basically like it's a big it's like a packet of 6 problems, and they're all word problems. So
Okay.
yeah. So the first one is pretty simple.
Mm-hmm.
Oil spilling from a ruptured tanker spreads out in a circle on the surface of the ocean. So
Okay.
the area of the spill increases at a rate of 9 pi meters per second, or meters squared per minute.
Now, do you notice why I wrote DADT?
Because you have to take the derivative of the
Well, when they say
area.
the rate that it's increasing,
Mm-hmm.
when you hear the word rate, you know it's a d something dt.
Okay.
In other words, if I'm moving along a highway at a rate of 40 miles an hour, then my ds dt is 40 miles an hour. That's a derivative.
Okay.
So rate always goes with the word derivative.
All right.
You said it was 9 square meters?
Yeah, meters squared per minute.
Okay.
And that's actually 9 pi.
9 pi. Okay.
Yeah. And then, how fast is the radius of the spill increasing when the radius is 10 meters, that is?
Okay. So, we need the equation that describes that circle.
Yeah. So that should be pi r squared, right?
Well, it's area equals pi r squared.
Oh, okay. All right.
Okay. And what we know is dA dt, so let's differentiate this thing with respect to t. What is it?
Well, the pi and the 9 are both constant, so it should just be 0, right?
Don't fill in the 9 yet. In other words, let's take our master, when with related rate problems, there's always a master equation.
Okay.
That we have to differentiate implicitly.
Oh, okay. All right. So, in which case it should be 2 pi, correct? Or
2 pi r, but because r is not t, I got to follow it with a dr dt.
dr dt.
Remember implicit differentiation, which is what you use on almost all related rate problems.
Okay.
Okay? And when you run into a variable that is not the variable of the denominator,
right,
you have to follow it with d of the variable you ran into relative to t, dt.
Okay.
Okay? So if that's true, that's true. In other words, I can implicitly differentiate both sides. Well, their question was, is the rate of the area change is 9 pi, so I can substitute 9 pi for that. And they want to know what is dr dt when r is what?
10. So we know 10. And then, pretty simple.
Now we have only one variable. In other words, now we only have one thing to solve for. That's dr dt. So dr dt would equal
9 over 20.
Yep.
Okay.
And that's the rate at which the radius is increasing with time. That's going to be a linear dimension. So that's got to be meters per minute.
Okay.
And that won't always be that way. In other words, when the radius gets to be 100, the dr dt may be different.
Okay.
It would be. It would be 9 over 2.
So why did you change the unit from meters squared per minute to meters per minute?
Well, because area is square.
Right.
In other words,
the radius is not.
Right.
Okay.
So radius is only going to change linearly, as a linear meters. In other words, you have linear measurements or meters, you have area measurements or square meters, and you have volume measurements or cubic meters.
Okay.
Okay. All right. So once I solve for dr dt, and the units would work out here, just in case you're wondering. Even if I put units on everything, this 10 is going to have a meters on it.
Right.
Okay, so the fact that this would come up meters per minute makes sense, because if we multiply it by 10, we're going to have meters squared per minute. And that's going to match the units on the left side of the equation.
All right. Okay. That makes sense. So that was surprisingly easy, actually.
Yeah, the key on all of these is to define your master equation, implicitly differentiate, and then plug in everything they gave you, and there'll only be one unknown to solve for.
Okay, so I think this one is like a similar gist. I think these all are, but a spherical balloon is inflated so that its radius increases at a rate of 2 over r. So that's 2 over r centimeters per second.
Now, I don't usually include units unless your teacher specifically wants you to deal with units. The units always are going to come out correct. And it just kind of complicates it. So let's try it without units. Unless they change up the units. In other words, if they say something's in inches or miles, then I'd have to put the units in. But as long as the units stay the same, we can leave them out. Okay?
And then the next part is, how fast is the volume increasing when the radius is 4?
So this is what they want to know. When r equals 4.
Right.
So what's the master equation that involves the volume of a sphere?
Isn't it like 4/3 pi r cubed?
You know that it's got to be cubed because we're dealing in volume. So we have to end up with cubic something.
Yeah.
Okay, and now with the second step?
You have to differentiate that, right?
Implicitly, with respect to t. And with related rates, it's almost always with respect to t. I mean, sometimes they'll give you a problem that's with respect to theta, but most of the time it's going to be with respect to t. So dv dt is equal to what?
Should be 4 pi r squared.
Interesting that that's the surface area of a sphere.
4 times.
So it's interesting that the surface area of a sphere is the first derivative of its volume.
Oh.
But in this case, we have to follow it with a dr dt.
Yeah.
Because we ran into that variable that was not t. Had that been t, we wouldn't have needed this.
Right. Okay.
It's only when you run into variables that are not the variable of the denominator that you have to always follow it with something.
All right.
Technically, we took the derivative of v, which was 1, and followed it with a dv dt. And that's how we actually got the left side of the equation.
Okay.
Okay. So they're saying, in this case, dr dt is 2 over r. And they want to know what dv dt is.
We're still left with a lot of variables.
Not really. 4 pi, because they wanted to know it when r was 4.
Oh, okay, never mind. Okay. I got confused. I didn't think we knew r for a second.
And dr dt is what again? It's 2 over r.
2 over 4.
And so we have 32 pi.
Oh, okay.
And we just, since that's a dv dt, then we know it's going to be in cubic something per second.
Right, okay. Yeah.
I don't know, was it in meters or centimeters? It was meters, so it's in meters cubed per second.
Cool. So yeah, I guess adding that third dimension didn't really change much on this problem.
No, it didn't. Yeah. The whole key is coming up with the master equation.
Okay.
I'll give you one that is going to illustrate something that's important. It took me a long time to learn. We have a ladder leaning against the wall. Yeah,
So is this the one where the ladder gets pulled back?
I'm going to make that 10. The ladder is slipping.
Yeah, okay.
Okay, down the wall at 2 feet per second. The question is what is the ladder doing there? How far along the base, at what speed is it moving?
Okay.
Okay, so let's make that y. Let's make that x. Let me erase that thing that I made look like an x. I don't want that. So that's the x dimension, that's the y dimension. That's the master equation that governs this. Because the ladder is always 10 foot tall, even as it slides down, it doesn't change its length.
Okay.
So what's the master equation?
Well, would this use sine and cosine?
No.
Or like
No, just the Pythagorean theorem.
Oh, okay, that makes sense. All right. So it'd be just x squared plus y squared equals 100, yeah.
Correct. Okay. So that's the equation that governs it. And they told us that it's slipping down at 2 feet per second. So that would be dy dt, would it not?
Oh, yeah.
And is it plus or minus?
It's negative. Yes.
Exactly. And it's negative not because it's moving in a downward direction. It's negative because the y dimension is decreasing. In other words, as this thing slips, y gets smaller.
Okay. All right.
So that's why it's negative. For a long time, I always thought that when it moved down, it was negative. When it moved up, it's positive. But this is a perfect problem to illustrate that's not true. What is dx dt going to be? Is it going to be positive or negative?
Oh, I see. It's negative.
No,
because
it's positive because x is getting bigger as it slips along the bottom.
Oh, okay. I see what you're saying now.
Okay, so the fact that it's going to the left does not make it negative.
So if it was upside down, it would be positive.
Right,
too.
but it's all about whether this is increasing or decreasing.
Right, okay.
This is decreasing, so it's negative. This is increasing. Our answer better be positive. What's our first step? Oh, well, first of all, they say that on related rate problems, also write what you're looking to determine. And we're looking to determine dx dt. So I'll put a question mark at that. And I need it at a specific point. So I'm going to say, what is it when x is 6 and y is 8? We're going to make that a nice 3, 4, 5 triangle.
Okay.
And these are always required because the rate that x is changing is constantly changing. Whatever we come up with it is going to be dependent on where the ladder is at any point in time.
Okay.
Okay, so let's implicitly differentiate this. What do we get?
This should be 2x times dy dt
times dx dt.
Oh, sorry, yeah.
Right.
And then plus 2y. And then I guess we have to do dy dt, yeah.
Correct, because y is not t.
And equals 0.
Exactly. And now notice what we have. We have dy dt. I can fill in for that.
Mm-hmm.
I can fill in for y. Y is 8. I can fill in for x. X is 6. And the only unknown I'll have left is what I'm trying to calculate.
Okay.
So let's do all that. X is 6, so I have 12 times dx dt. And that's going to be equal, I'm going to put this all on the other side. Y is 8, so it's minus 16 times a minus 2, which is dy dt.
Okay.
Okay, so when I do the algebra, I get dx dt equals plus 32 divided by 12. So that is the rate that x is changing per second. That many feet per second. And it's positive because x is increasing, not because it's going to the left.
Okay.
Okay, all right. I like to illustrate this problem because it really illustrates the sign. The sign is tough to grasp on these things as to whether it's positive or negative. And it's positive or negative depending on whether that dimension is increasing or decreasing.
Okay.
Okay.
So this one has a bit more variables.
Okay.
I wasn't really sure how to incorporate all of them. So a 7-foot tall person is walking away from a 20-foot tall lamppost.
Oh, I love this one. How fast is his shadow moving?
Yeah.
7 foot tall?
And that's happening at a rate of 5 feet per second.
That he's moving away?
Uh-huh.
Okay, we're going to make this x. In fact, let's put this on a xy coordinate system. So we know that dx dt is plus or minus. Which one?
Well, it should be plus.
Plus what? 5?
Yeah.
A fast walker. 5 miles per hour or 5 feet per second?
5 feet per second.
5 feet.
Which is ridiculous, yeah.
That's pretty fast also.
Yeah.
I mean, most people walk at about 3 miles an hour. I can't imagine 5 feet a second. No, maybe you can do that. That's probably realistic.
Yeah.
Okay. And what do they want to know?
And it says, assume the scenario can be modeled with right triangles.
Okay.
And then it says, at what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost?
Okay.
Yep.
X is the distance from here to here.
Okay.
Okay. So, ooh, interesting. So this distance of this triangle is 16 minus x, or x minus 16, excuse me.
Oh, so x is the whole...
Yeah, x is the whole triangle.
Okay.
The whole base. So this dx dt is not right either. Let's change that. Okay. They want to know how fast his shadow is changing. So they want to know dx dt, right?
Uh-huh.
That's what we're trying to figure out.
So the dy dt would be the... No, it actually wouldn't.
No, let's see. The information they gave us is that let me think about this a second. It's a little bit different. Well, let's see. We have a couple of equations here. We have 20 squared plus x squared equals z squared. That's the big triangle. And then we have, that's the large triangle.
Yeah.
And in the smaller triangle, we have 7 squared plus the quantity x minus 16 squared equals
z over...
I'll use a different variable for the moment. I'll use d squared. Let's use h, the hypotenuse.
Okay.
Now, how do we incorporate the information that he is moving at 5 feet per minute? That means x is doing dx dt is the movement of the end of his shadow. Ah, these are proportional. These are similar triangles.
How did you know that?
Well, they just are by definition. Whenever you have something like this, and these two lines are perpendicular or parallel, and you know the lamppost is standing at a right angle to the ground, and he is standing at a right angle to the ground. So this angle is the same, and this is similar to that because this is parallel to that, so that angle is the same as that angle. And this angle is the same as that angle. So you have all three angles are the same, which makes it similar.
Oh, is that like proving it via the geometry proofs, like the side angle? Okay.
Yeah, exactly. So what does that mean? That means that 7 is
the equations equal to each other, right?
Well, 7 is to 20 as x minus 16 is to x.
Oh, okay. All right.
Now, still don't know how to incorporate his movement of 5. What would that be? That would be...
Oh, okay. Well, there's a little hint on the back page.
What is it? Yeah, that might be helpful.
It says the equation is x plus y over 20 equals y over 7.
X plus y...
I guess they're making z y?
Oh, okay. So...
Maybe. That's just a guess, though.
X... What'd you say again?
Oh, wait, no. They're defining y as the length of the shadow. Oh, yes, so that is right.
Oh, that's what we want to do. That's what we want to do, is we want to make that x and that y.
Oh. Okay.
Yeah. Okay, and now, what's the hint they gave you?
Sorry, let me get to it. Okay, x plus y over 20.
Okay, that's the base of the big triangle over the height.
Is equal to y over 7. Yeah, okay. That makes sense.
The little triangle over its height. Okay. Yeah. Now we have an x and a y, and we know what dx dt is 5, and we're trying to solve for dy dt. Okay. So the first thing we have to do is implicitly, let's cross multiply this.
Okay, all right.
Make it a little easier to deal with. So we have 7x plus 7y equals 20y. Okay. Now let's move the y to the left. So we have 7x minus 13y equals 0.
Oh, okay.
Now let's implicitly differentiate it. What do you got?
Well, it should be 7, 9, no. I'm drawing a blank on this. Wow. Okay.
We ran into a variable that was not t.
Yeah.
So we have to follow it with a dx dt.
Oh, okay, you just get rid of the x, right? Okay.
Same thing here. We ran into a variable that is y, which is not t, so I have to follow it with a dy dt. The other side is still 0.
Okay.
They gave us dx dt, is all we have to do is solve for dy dt. Dx dt is going to be...
Is that the 5?
Well, let's see, they gave us dx dt. Yeah, that was plus 5. 7 times 5. And that's equal to 13 dy dt, which is what we're trying to calculate. So dy dt equals 35 divided by 13. I don't like that answer. It's not so bad, I guess. The reason I didn't like it at first was because the shadow has to be moving faster than the person. Because as the person moves to the right, this angle changes. Right?
Yeah.
And the length of the shadow gets longer. In other words, whatever the length of the shadow is here, as that person moves to the right, the shadow is going to get longer. Try it sometime.
Okay.
Go out when the sun is at an angle and measure your shadow and then walk away from the sun, and your shadow will get longer. It has to. In other words, imagine the scenario here. If I draw this picture and he has walked for a long while, now the picture looks like that, and he's standing right there. There, he's 7 foot tall. This is 20, but this angle is bigger, which means this angle is smaller, which means this distance
is bigger.
Well, yeah. In other words, however fast he's moving to the right, if his shadow is getting longer, then his shadow has to be moving even further, even faster. Now, I didn't like the answer I came up with because it's almost
less
3. It's less than 5. But notice what that is. That's the change in y. The actual speed of that point of his shadow is the change in x plus the change in y.
Oh, okay.
In other words, this point of his shadow...
It does actually make sense.
Yeah, it does. So his shadow would actually be moving at 5 plus 2 and change, or almost 3. So his shadow is going to be moving at closer to 7 or 8 miles per hour, or feet per second. Which brings up the interesting physics question. How fast would he have to move before his shadow was moving faster than the speed of light?
Okay.
You see why that's an interesting question? Because nothing moves faster than the speed of light. You can't move faster than the speed of light.
But your shadow can. Wow, that's
well, maybe. The speed of light's also going to have to do something with the light traveling from the light pole to the point of his shadow. So relative physics probably enters into this equation. But
has lots of real-world application, this one.
Yeah. The fact that his shadow is moving about 50% faster than him means he would only have to go about 3/4 of the speed of light.
You make it sound so easy.
His shadow was actually going faster than the speed of light. But I'm sure relative physics restricts that and enters into the formula. But yeah, no, this is a good problem. It's always a lifeguard and a light pole is the way I've always heard it put. But this is a toughie. The hint they gave us was helpful. Using two variables, x for that and y for that.
Yeah.
Because then you can set up that proportion because of the similar triangles. Then you have two variables you can differentiate. You're going to have a dy dt and a dx dt. And those are the two key numbers, the only two key numbers we have. This was a little different than the others because they didn't say, well, I guess they did. They said when he was 16 feet away.
All right. Okay.
Hold on a minute. And there is no x or y in our differentiated equation. So we don't need that number. Huh.
Well, that's very like our math teacher to give us stuff that we don't need, though.
Well, I'm a little disturbed by the fact that I'm going to come up with the same answer regardless of how far he is from the light pole. In other words, even if he's 30 feet away from the light pole, it's not going to change our answer. And it feels like it should. But when we differentiate this equation, the x and the y go away. I mean, we're left with a dx dt and a dy dt, but we don't have an x and y anymore. If we still had an x in the equation, we would substitute 16 for it. But maybe that's correct. Yeah, no, it could be correct, and she just gave you that 16 and it doesn't really have any bearing on it.
Yeah.
All right, what else you got?
Well, it is 8, but if you would be fine with helping me set up this last equation, and then maybe I could do the rest by myself.
Yeah, that's fine for sure. Yeah, okay. I don't mind going a few minutes over. I love the.
All right. Yeah. Okay. So an observer stands 700 feet away from a launch pad to observe a rocket launch.
This is going to be an angle one.
Okay. All right. Gross. The rocket blasts off and maintains a velocity of 900 feet per second.
Okay, so dy dt is 900 feet per second. Okay.
And then assume the scenario can be modeled as a right triangle.
Mm-hmm.
How fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground?
That's actually dz dt is what they're looking for.
Oh. Okay.
Right? It's not an angle problem. Usually the question on a rocket ship problem like this is, how fast is this angle changing? If the rocket's moving at 900 feet per second, how fast is the angle changing? And then we would set up that angle is the inverse tangent of y over 700. And we would have to differentiate an inverse tangent function. But this is a little easier. We can call that z, we can call this y, and we can call this x. So what's the master equation?
Well, it's Pythagorean theorem again, right?
Yep.
So it should be 700x.
No, not 700x, just x squared.
Oh, all right then.
In other words, we're going to fill in the 700 after we've implicitly differentiated.
Oh, okay. All right.
Okay, so our master equation is just this. Implicitly differentiate that, what do we get?
Well, just 2x, 2y, 2z.
dx dt.
Oh, yeah. Mm-hmm.
And that's the critical part of the equation, actually, is that time equals 2z dz dt. Because that's a variable that's not t, so I have to follow it with that.
Yeah.
Okay, now, what do we know? We know dy dt is 900. So I can substitute, let me write one more step here. X is 700, right?
Yeah.
dx dt, we don't know what that is. They didn't tell us that. That's because it's not changing.
Oh, so it's just 0.
Yeah, it is 0.
Oh, yeah, that makes sense, because isn't it like...
Yeah, dx dt is not changing, so the rate of change of x is 0.
And wouldn't that also be just like you can take the derivative of 700 and it would be 0?
I guess. I did it this way for a reason, is that they want to know when it's 700 feet away, and typically you fill that in for x.
Right.
Okay? And we just have to realize that dx dt is 0. We can see from the model that it's got to be 0.
Yeah.
It doesn't change as that rocket heads up. It's always 700 feet away. Okay? But 2y...
Well, do we know why, per se?
Did they tell you when the rocket is at a certain height?
Actually, yeah. Yeah, how fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground? Okay, I thought that was z, but no, it's y.
So 2,400 is what we're going to fill in for y. And dy dt is 900, positive. And z, we have to use the Pythagorean theorem to figure out what it is, but we're trying to calculate dz dt. Well, what is z when x is 700?
Oh, God, I don't know.
Well, okay, yeah, I'm just, in other words, you're going to solve that Pythagorean triangle, and that's what you're going to fill in for z, right there.
Right. The
square root of 2400 squared plus 700 squared.
Which ends up being 2500, so we're something.
Okay. Oh, yeah, that's a 7, 24, 25 triangle. So 2500 is there. Notice that disappears. You only have one variable, dz dt.
Okay. I think I could take it from there.
Yeah. Just multiply that out, divide it by 5,000, and you have your answer. And it's positive, which makes sense, because as that rocket's going up, z's getting bigger.
Right.
So dz dt should be positive.
Okay. This is good. This is one of the few calculus concepts I feel like I really understand.
Well, this is one of the harder ones. As far as differential calculus related rates, I put right up there at some of the tougher differential calculus questions. Also, optimization problems. I don't know if you've gotten to those yet.
No, we haven't.
That's coming next, and those are about equally difficult.
Okay.
Okay? All right, Brent. Have a good evening.
Thanks for your help. This was a really helpful one.
Good. Okay, I'll talk to you next time.
Okay, you as well.
Bye-bye.